So all you have to do is just make a list. Here. So whatever you found is fine. And then the same thing, list all the anions that you found. That is, you got a positive test for it. Okay. Were there any other questions?
I'm still seeing chapter 20 and 19 homework Thursday.
Yeah. Chapter 20 and chapter 19 homework are very well. Chapter 19 homework I'm almost done with, actually. Finish it tonight. And then chapter 20, yeah, that would be due Thursday. There's also some from a very few problems from 24 and 25 you can turn into, we'll go through those ones as well. So you know what might. I'll talk about 24 and 25.
And then are we just turning in our lab notebooks as is, just like what we did in lab?
Yeah. I'll just check it off during the exam.
Oh.
So I'd like to see your lab notebook as well.
All the other labs due tomorrow or Wednesday?
Okay, the other labs I can have due on probably either Friday, after the exam. You could turn them in whenever. You could turn them in now, or on Thursday with our final, or you can turn it in on Friday or Monday at the latest after the test. No, I need a hard copy of that. And so if it's on the Friday, you just drop it off at the office there, and then ask them to put it in my mailbox. And then I'm going to pick those up on Monday. So if you get it in before Monday, probably Monday evening, I'll come by and pick up any late labs. Okay, that goes for all late work will be turned in, will be due probably on that Monday, including homework if you have it. You guys are almost done, or you're done with the pH and the synthesis?
Yeah. Okay. Yeah, fully done with pH, like 90, 95%.
Yeah, you can turn it in after finals. Just get it in by Monday. Okay, other questions? All right. So I'm going to finish up chapter 20 and then talk about 24, 25 a little bit. It's not much. It's just going to be based on the PowerPoint. I don't have to do too much for those particular chapters. So one example of a voltaic or, voltaic cell or a battery, although this doesn't look like a battery, it's corrosion. When we look at corrosion, corrosion is a lot more complicated because normally when we think about iron rusting, this is the way I usually think. I have two irons and then three oxygens combined to form Fe2O3. Fe2O3 is rust. But it turns out that this process is more complicated than that. Because if it were just oxygen attacking the iron, then this is an extremely slow process. And take a long time for things to oxidize. But usually rust happens very fast. And when we look at the process itself, it turns out it's just a battery, essentially. There's the voltage for this battery. So if if we look, oxygen has a half reaction here, except this is in water. This is not an acid, so actually, or basic solution because we form hydroxide. And so if we look at oxygen in water, it takes up 4 electrons to form 4 hydroxides. And then iron loses those electrons. So we're rusting iron. So essentially oxygen is taking electrons from iron. In that process, it's making iron 2. And so initially what we form is iron 2 and hydroxide. You can see here, if we put some phenolphthalein, this is a nail, and the ends of the nail have been hammered. And what we can see is we see a lot of pink color indicating a lot of hydroxides being generated there. So the oxygen is coming in and taking electrons from this part of the nail. But where are those electrons coming from? Those electrons are coming from the hammered ends. In the hammered ends, the iron is distorted. The structure of the iron is distorted, and there are a lot of defects in there, and so it's more susceptible to oxidation than the pristine part of the nail here. And so it's hard to see, but there's green here. Green precipitate here, and green precipitate here. So what's happening is the iron is being oxidized to iron 2. And so iron 2 doesn't get very far before it's attacked by hydroxide. So the hydroxide moves a lot faster because it's a lot lighter. So the hydroxide diffuses quite fast over here and precipitates the iron as it's being formed. But overall, this is still somewhat slow because, you know, we don't have a salt bridge here. And so what we have to do is we have to wait for the anions to come over to the anode to help neutralize that charge. And then as the anions migrate here, that's going to help alleviate the negative charge buildup at the cathode here. And so this is rusting of iron here. This shows 1 cathode here, 2 anodes. Over here, if we bend the nail here, this is going to show 3 anodes. You see the green precipitate there, and 2 cathodes here. And so if there's like, for example, if you dent one of the fenders in a car or something like that, then it's susceptible to rust, the defects. Now, since this is basically a battery, if we had a salt bridge, that would help. It would help speed it up. When we did it in the lab, and we removed the salt bridge, that was in 2 separate beakers. This is in 1 beaker, the anode and the cathode. So if we have salt water, then that's going to help neutralize the space charge. There's a lot of negative charge buildup here and positive charge buildup here. So with salt water, will help neutralize the charge, and that will speed it up. So rust happens a lot faster in salt water because salt water acts as a salt bridge. Rust also happens a lot faster in acid because in acid solution we have a different reduction potential. That is, if we have acid, H+, we end up forming water as a product versus hydroxide. Water is a lot more stable product. And so if you look at the reduction potential, it's almost, it's 1.2, a little over 1.2 volts in acid versus the reduction potential in water. The reduction potential in water is 0.4 volts. So it's 3 times bigger reduction potential in acid. And so 1.2 plus 0.4 is going to give us about 1.6, 1.7 volts in acid versus 0.8 volts in water. And so rust and corrosion should happen much faster in acid solution. Okay, that's some corrosion. There's ways to try to prevent corrosion. One of those is called cathodic protection or sacrificial anode. We don't want the iron to corrode because that's structural, you know. And so what we do here is we use something else with an even higher potential. Oxidation potential. Something else that has a higher oxidation potential would be zinc. Zinc has a higher oxidation potential than iron. So you can see some zinc foil wrapped around here. And so what that means means is that the iron turns out to be the cathode. You can see the hydroxide being generated there, and the zinc is the new anode. And so we call it sacrificial anode because the anode is what gets oxidized, and zinc is easy to oxidize, and we'll replace the zinc instead of the iron. Now, the zinc is not a non-structural material, so the nail is going to retain its structural integrity, whereas the zinc will be eaten away. And so this is the whole process of galvanizing. Galvanizing is you put a zinc coating on there, and the zinc acts as a sacrificial anode, an anode that you don't care about. And, but we do care about the iron, protecting the iron, so that protects the iron. Over here we see galvanized nails, and these nails have been dipped in zinc. Here on boats, they don't dip it in zinc. Instead, they use sacrificial magnesium anodes, so there's just magnesium attached to it. Magnesium has a higher oxidation potential than steel, and so the magnesium is oxidized first. It sits in salt water. And so the sacrificial anodes, these are replaceable because they're going to be eaten away. You know, eventually all the zinc will get eaten away, and then the iron will start to rust. When that happens, then we'll lose the nail. But over here, these magnesium anodes can be replaced. They do this for gas lines also. In gas lines, you can go to Home Depot and you can buy sacrificial anodes. They sell them there. You can protect your pipes with sacrificial anodes. And the other way to protect iron is to paint it. If you paint it, you make a protective barrier so that the oxygen can't get through to oxidize the iron here. But the problem with paint is if there are any chips in the paint, then it's going to start rusting where there are chips in the paint. Or you could use some other inert coating like copper. But copper is not very effective for the same reasons. If there's chips in here, then the underlying iron will be oxidized. Copper has a much lower oxidation potential than iron. So since iron has a much higher oxidation potential, it's going to be oxidized, and that's what we see here. If you wrap an iron nail with copper, then the iron is going to be the anode, it's going to be oxidized, and the copper will be the cathode, it will stay there. So you can see all the hydroxide generated at the cathode. And then we see the green precipitated iron 2 hydroxide. Now, iron 2 hydroxide was produced initially, but eventually that iron 2 hydroxide is going to be oxidized further to iron 3 oxide. This. And so that's just going to be from air oxidation. So we form iron 2 hydroxide from these electrochemical processes, and this is going to be oxidized further. This is just a symbol for oxidation. And in this case, it's going to be oxidized by air. You know what the symbol for reduction is? It's just an H instead of an O. Symbol for reduction. So this is like the Statue of Liberty's iron with a copper coating, but all the iron has been eaten away. So this is the copper thin film of copper, just with the skeleton eaten away, so the thin skin of copper. Okay, so that's corrosion. Corrosion is important. Okay, the next thing we're going to talk about in chapter 20 is electrolysis. There are 2 types of cells. There's the voltaic or the galvanic cell. The voltaic or galvanic cell generates electricity. And the other type of electrochemical cell is the electrolytic cell. The electrolytic cell does the opposite. And so a galvanic or voltaic cell converts chemical potential energy into electricity. An electrolytic cell converts electrical energy into chemical potential energy. So what we can do is we can synthesize higher energy, unstable chemicals this way. And so one example of that is just recharging the battery. And so normally the electrons flow left to right. This is the anode, this is the cathode over here. But if we hook up a battery, the positive is given to the cathode. And so this would be the cathode of the battery. The anode is where we generate electrons. This would be the anode. So at the positive cathode of the battery, we hook this up to this electrode here. And what we do is we turn up the voltage. If we turn up the voltage high enough, then we can oxidize something that's in contact with the anode. So in this case, we'll oxidize the copper to generate more copper 2 over here. And then this becomes the anode. And then we force electrons over here, and we'll end up reducing. So we'll end up reducing the zinc ions back to zinc. And so we just reverse the reaction in this particular case. So the reaction was this. The zinc solid plus copper 2 plus makes zinc 2 plus copper solid. And so by using electrolysis, we can force this to go backwards in an unfavorable direction. Here. So this is about 1.1 volts, and so to reverse it, we need to put more than 1.1 volts. There's something called the overpotential where we have to add. So if it generates 1.1 volts going left to right, then to stop it would require 1.1 volts, but to force it in the backwards direction requires greater than 1.1 volts. And so an electrolysis would apply a potential greater than the cell potential. To force it backwards. And so we're just forcing the electrons to go backwards in the circuit, and that reverses the reaction. Some reactions are easy to reverse, other reactions are very difficult to reverse. So not all batteries are rechargeable, and therefore rechargeable batteries are called secondary batteries. Primary batteries are batteries that in general are not rechargeable. And so we have primary batteries, secondary batteries. This would be an example of a secondary battery because this one can be recharged without too much difficulty. So that's one application of electrolysis. Another application of electrolysis is generating unstable chemicals. This would be the electrolysis of water. And so what we do is we hook up, let's see which one is the anode and which one is the cathode. When we do electrolysis, we're taking water and then we're forcing the oxidation of something in the water and forcing the reduction of something in the water. And so if we look at water, H2O, the oxidation state of hydrogen is +1 and the oxidation state of oxygen is -2. So if we're to oxidize water, we're going to take electrons from oxygen. If we take electrons from oxygen, that's going to produce O2 gas. If we force the reduction, so this would be the oxidation of water. If we force reduction of water, that's going to generate a hydrogen gas because we're going to give the electrons to hydrogen, and that's going to make H2 gas. And so over here, which one is which? If you take a look, which one is which? Well, when we look at the ratio, we generate twice as much hydrogen gas as oxygen gas. So over at this electrode, we must be generating the hydrogen gas. In other words, the electrons are being forced in here by the power supply. This is a 9-volt battery. You could do this with 9 volts. And so electrons are being forced in here, and then the hydrogens are being reduced. The hydrogen atoms in water, and then we're generating hydrogen gas. Over here, we must be pulling the electrons off. So the electrons are being pulled off here and being forced into the battery. And the electrons, we must be oxidizing something. And in this case, we're oxidizing the water. The water is both a reducing agent and a non-oxidizing agent. So in this case here, hydrogen acting as a reducing agent. We got the reduction potential here, 2 electrons is going to form H2 gas. Water acting as the, well, here's the oxidation of water. The oxidation of water forms oxygen, the reduction of water forms hydrogen. Overall, reaction is water, 2 waters goes to 2 hydrogens plus an oxygen. The hydroxide and the hydrogen here ions react to form water, and those will cancel out here. And the cell potential, we can calculate by getting these values. These values in the chart, we get minus 2.06 volts. And so what that means is this is unfavorable. So what we have to do is we have to force this backwards. And so we have to apply at least 2.06 volts. In fact, we have to apply more than 2.06 volts. 2.06 volts isn't enough. Now this is a 9-volt battery here, but we need at least like 5 volts or something. It depends. And that's the over potential happening there. So basically, this one, you know, the symbol, I wanted to point this out, is the symbol is inconsistent sometimes, you know, because how people like to do the sign of the electrode up here. And so normally, okay, this is the cathode of the power supply of the battery. And this is the anode of the cell, the electrolytic cell. So normally the anode gets a negative sign here. And so this would be, you hook up the positive to the negative here. And then the negative to, this would be the cathode, so this would be positive over here. But it depends on who does this, because a lot of people, what they'll do is they'll say this is positive and this is positive. But normally we don't think of an anode as being positive. Positive is pulling electrons in. Negative is generating electrons. And so you have to be careful when people are talking about the sign on this. You know, but the anode is always where oxidation occurs, and the anode is always where we generate electrons. So I don't, you know, I like to be consistent. I don't like to mix things up, and a lot of people like to mix it up. And so the anode, we're generating electrons. If we're generating electrons, the electrode should be negative, but here they're calling it positive, even though we're generating electrons here, because the reason they're calling it positive is because you hook it up to the positive terminal of the battery or the power supply. And so this is the reason they're calling it positive, but the actual cell itself, it would be negative. And so they're calling it positive because we're hooking it up to the positive terminal of the battery or the power supply. It could be a 9-volt battery or whatever. But actually that electrode should be negative, because anodes are where oxidation occurs, always. That never changes. So the anode is where oxidation occurs. And oxidation, we're generating electrons, so it should be negative. But anyway, the whole point of this is a lot of stuff, but basically all this says is that in voltaic cells, it's spontaneous. Delta G is less than 0. In electrolytic cells, it's non-spontaneous, so we need external power source to get it to go. And so don't worry about this bottom thing. I don't pay much attention. Otherwise, just be careful with the sign. Note that the sign of each electrode in an electrolytic cell is the same as the sign of the battery electrode to which it is attached. So they're just trying to make it easy, I guess, in that way, but it makes it confusing because it's inconsistent for me. And so basically most people don't really worry too much about the sign. So there are applications of electrolysis. One is electroplating. You get electroplate or refining copper. Here's a rack of things. So we can put a chrome plate on there, or a copper plate on different things. You use electrolysis. We're generating elements, you know, that are normally unstable, like chlorine gas and sodium. This is electrolysis of sodium chloride, AQ. Sodium chloride AQ, actually this is not sodium chloride AQ. As if it were AQ, we can't generate sodium unless we protect it somehow. And this is actually sodium chloride AQ. The way it's protected is there's mercury, liquid mercury, and the sodium metal it's generated gets, dissolved in the liquid mercury to protect it. Otherwise, if sodium came into contact with water, it would immediately generate hydrogen gas. And so normally when we do electrolysis of aqueous sodium chloride, we generate hydrogen gas and chlorine gas. Actually, we generate some hydrogen there, but sodium. Actually, they're letting the sodium hit the water. talk a little bit about electrolysis, so we can make some predictions about what, you know, what we oxidize, what we reduce. We oxidize whatever has the highest oxidation potential, you know, that's in contact with electrode. We reduce whatever has the highest reduction potential when it's in contact. And sometimes we have a choice. So let me just do a quick thing here. So the key things to clean, we don't want the electrodes to react. And so we need inert electrodes when we do electrolysis to generate, you know, higher energy chemicals. And so inert electrodes, the two most common ones are platinum or graphite. And then we'll have a power source here, and we force the electrons to go right to left, backwards. Platinum or carbon solid. And so to keep this clean, we could electrolyze like sodium chloride liquid. This is molten sodium chloride. So over here, we're going to oxidize something. So this is the cathode of the power supply that is hooked up to the anode of our cell. And so oxidation occurs at the anode. And so in this case, what's easiest to oxidize? It turns out that chloride is going to be the easiest to oxidize. And chloride will have a higher oxidation potential than platinum or carbon. And so the species with the highest oxidation, and sodium ion isn't oxidized. So the species with the highest oxidation potential is oxidized. So we'll generate chlorine gas here, plus 2 electrons. And the chlorine gas will be generated here. Over here, we're going to reduce, you know, whatever has the highest reduction potential. And so when we look at it, the highest reduction potential is going to be sodium ions. So we can just look that up on the chart, and this will form sodium liquid. So the sodium liquid will float to the surface here. We've got to make sure we have a barrier so the chlorine gas and the sodium liquid don't come into contact. If we put water, like say, you know, this is molten sodium chloride, but if we have sodium chloride aqueous, it could change what products we end up getting. Okay, so if we repeat this with, let's use platinum here. Platinum here. We'll hook this up to the power supply here. So we're going to force electrons in, and we could change the voltage here. The voltage is adjustable. And so we can just keep increasing the volts until we oxidize something and reduce something, so we can force the reaction to occur. And so over here, this is going to be the anode of our cell being hooked up to the cathode. The cathode is pulling the electrons in, and so the anode, something's going to be oxidized. And so we look at what we have that could be oxidized: platinum, sodium, chloride, and water. And then we look at the oxidation potentials for these. Now, the oxidation potential for platinum, unfortunately, isn't on this. I went through this on the homework also. And so I think gold would be comparable to platinum. So if we have gold here, the oxidation potential for gold, which would be the reverse, would be negative 1.52 volts. And so gold and platinum are similar in that respect. And so negative 1.5 volts means it's not very susceptible to oxidation. So since we don't have gold, it's negative 1.52 volts. And so it should be comparable to gold. Sodium ions are going to have a very, very low oxidation potential because sodium ions already lost its valence. And so in order to oxidize sodium ions, we have to oxidize a core electron and make Na2 plus an electron. Oxidizing core electrons, if you recall from Chem 1A, cost about 10 times as much energy as oxidizing a valence electron. And so those are very, and so this one is so low that we typically just ignore it. And then chloride, the oxidation potential for chloride is sorry, I need to check this.
There's 4 atoms there. 4. Crystal violet synthesis, hydrogen, and
Oh, yeah, I read too, sorry.
What hydration?
I thought you just heard
crystal violet.
Oh, it's a total, sorry.
I already did something somewhere.
Okay. We got, sorry.
Very simple.
So we'll look for chloride here. And chloride is negative 1.36 volts. Negative 1.36 volts, the oxidation potential. And then water oxidation potential is here, negative 1.229 volts. Negative 1.229 volts. So which species has the highest oxidation potential? Water. Water has the highest oxidation potential, so water is going to be oxidized. If water is oxidized, what gas do we form here? Oxygen. So we're going to generate O2 gas here. And the reaction, we can just copy off this chart here. And the reaction is water is oxidized to O2 gas plus 4H plus 4 electrons. This is the reverse of this. Okay. Over at this electrode, we're going to reduce something. And what we're going to reduce is the species with the highest reduction potential. And so over here, this would be the anode. And this is going to be hooked up to the cathode of this. So what can we reduce? Platinum is not really a great candidate for reduction because if platinum gets reduced, we'll form the PT minus anion. PT minus anion, have you ever heard of it? That's probably a good reason. It's not all that stable sense of this. And so if it's not that favorable, then its reduction potential should be very low. Right? And so what we'd say is that platinum should have a very, very low reduction potential. So it's something that we can ignore. And then we look at sodium ions. We could reduce sodium ions. What's the reduction potential for sodium ion? Well, sodium ion is not that great, but it's negative 2.714 volts. So sodium ion is negative 2.714 volts. And I'd expect platinum to be lower than that. And what else can we reduce? Can we reduce chloride? Chloride already has a filled valence shell. So if chloride picks up another electron, where does that extra electron go? So if chloride already has a filled valence shell, has an octet, then adding an extra electron, that extra electron is going to go into the next energy shell. We go into the fourth energy shell. And so this is going to be very, very low. You know, chloride's not a good oxide. Chloride's happy as is. You know, it doesn't want another electron. And so what else do we have? We have water. And so what's the reduction potential for water? And so we'll go down here. Well, let's take a look. For water, we have this one here. So two water picks up two electrons to form hydrogen gas and hydroxide. And that's actually negative 0.828 volts. Water. If you recall the chart I gave, let's see if I have that here. If you look at the chart I gave, this is the chart you'd use on the test anyway. Probably should use this. To sign in here. Water is at the bottom of the chart, but it's not the weakest oxidizer. If we look at its reduction potential is minus 0.8 volts. Minus 0.8 volts puts it between zinc 2 and aluminum 3. That's what these three dots indicate. These three dots mean we put water there. And that's going to be between minus 0.7 and minus 1.6, closer to minus 0.7. And so water fits there. So which one has the highest reduction potential here? Water. And so you know what we're going to generate at this electrode? H2 gas. So take a look at the total. It's completely different. I mean, if we have molten sodium chloride, we're going to generate sodium and chlorine. If we have aqueous sodium chloride, what are we going to generate? Hydrogen gas and oxygen gas. And so it makes a huge difference as to what we form. Okay, but there's one issue. And there's one, this is the only complication that you have to know. Okay, so this is what we predict. The issue is this. If we look at go back here and we look at the oxidation, we decided we're going to oxidize water because water has a higher oxidation potential. Negative 1.2 is higher than negative 1.36. And that's the case here. But this is the one exception that you need to know, and that is the activation energy. You know, the activation energy to oxidize water is pretty big, because in order to oxidize water, what do you have to do? You have to kind of break the bonds and then make hydrogen. So we have a water, we got to break it apart, the hydrogens from the oxygens, and so the activation energy is kind of high. But if we oxidize chloride, what do we have to do? If we oxidize chloride, we just have to pluck an electron from the outermost shell. And so the activation barrier is not so very big there. And so even though it's more profitable to oxidize water, kinetically it's just a lot easier to oxidize chloride, because we just pluck the electron off. We don't have to break bonds and do that kind of stuff. And so this is the one exception. We predict we're going to form oxygen, but we don't. Here. And that's because this is the one exception because everything else works, this is fine. And this should have worked except this big activation hump here. And so what ends up happening, and it depends on the overload that you put in there. What ends up happening is this is kinetically much easier to oxidize. And so it's going to happen faster, kinetically. Easier. Probably not the correct wording on that. And so even though we predict water to form oxygen, it's going to be chloride, and we actually generate chlorine gas at this electrode. This is the only exception. The only exception is water versus chloride. Which one's easier? Chloride's easier to oxidize, even though it has a slightly lower oxidation potential. And so this is the one exception that we need to know for electrolysis. Chloride versus water, and we're looking at oxidation. We predict water, but turns out that chloride, because of kinetics. Chloride is oxidized. Otherwise, everything else works. So here we can see we generate chlorine rather than oxygen gas. All right, the final part of chapter 20 is stoichiometry. We use electrochemical stoichiometry with both electrolytic and voltaic galvanic cells. It's the same. The only thing we need to know is something called current. Current is defined by this quantity. It's amperage or amps. So when we're looking at electrical current, that's amps. And 1 amp is defined as 1 coulomb per second. 1 coulomb of charge per second. And so we use that as a conversion factor. Yeah. And so if we know what the current is and the time, we can figure out how many total coulombs of charge pass through the circuit. And then we can use Faraday's constant to convert that to moles of electrons. And so typically we start off with time. Time times amperage gives us coulombs. Coulombs can be converted into moles of electrons. Moles of electrons can be converted into moles of product if we know the balanced half reaction. And so balanced half reaction would be something like this. We can figure out how many grams of chlorine gas are produced. And so the typical currents are milliamps. And the time, let's say we did an example here. We did 60 minutes, 1 hour at 100 milliamps of current. It's a symbol A. And we want to know how many grams of chlorine gas are produced in this electrolytic cell over here. And so we do 60 minutes and then convert that into seconds. Do 60 seconds per minute. And then we have 100 milliamps. That would be 0.100 amps. And so that would be 0.100 coulombs per second. 0.100 coulombs per second. So minutes cancel, seconds cancel, and that gives me the total number of coulombs of charge. So if we know the total number of coulombs of charge, then we can figure out how many electrons. Because there's 96,485 coulombs of charge for 1 mole of electrons. And then if we know how many moles of electrons, then we look at the balanced half reaction. That is, in this case, we have chloride being oxidized. So 2 chlorides are oxidized to chlorine plus 2 electrons. So for every mole of chlorine, we consume 2 moles of electrons. And so for every 1 mole of chlorine produced, we have 2 moles of electrons consumed. And then chlorine weighs 70.90 grams per mole. And so that'll give us how many grams. So let's calculate how many grams. So it's 60 times 60 times 0.1 divided by 96,485 divided by 2 times 70.9. 0.132 is 0.13227 grams of chlorine gas are produced. So how many sig figs? So we'll make it 2 sig figs, so we'll go 0.13 grams of chlorine gas. So that would be an example. You could do this in either type of cell, electrolytic or voltaic cell. You just need to know the flow, the current flow. And you can measure the current flow using an ammeter. That's chapter 20. Then 24 and 25 are just kind of surveys of rough. We looked at isomers earlier, and there are different kinds of isomers. There's things called structural isomers. So, for example, these would be structural isomers where, let's say I have ammonia, 5 ammonias and 1 sulfate. These are ligands here, and then chloride would be a counter anion. So there's a pentamine, sulfato, chromium 3 chloride. But if I look over here, we'll have sulfate. So now we have 1 chloro ligand and 5 amine ligands. So this would be pentamine, chlorido, chromium 3 sulfate. Essentially, it's made up of all the same things, but structurally it's different because here the sulfate is bonded directly with chromium. Over here, the sulfate is just a counter anion, just an anion. So these are called structural isomers here. And then different types of structural isomers, but I don't worry about them. They're just all structural isomers. Here's some more structural isomers here. Here if I look at cobalt, I have the mean complex of cobalt over here. Over here I have the mean complex of chromium. And then over here I have a cyano complex of chromium, and here I have a cyano complex of cobalt. So it depends on how you write the formula. Both of these consist of all the same elements. So these would be structural isomers, but structurally they're different. This would also be a structural isomer because this is a nitrito ligand with the N bonded as the donor. This would be a nitrito ligand with the O bonded. And so essentially these are the same, except this one has an oxygen bonded to the cobalt and nitrite, and this one has nitrogen bonded. Again, structural isomers. What we spent our time looking at are the stereoisomers. Stereoisomers, like the right speaker and the left speaker, they look the same, basically, but they're positioned differently in space. So we have cis-trans isomers. Cis are adjacent, this, trans are opposite. These will show, you know, based on the structure, they're going to show different boiling points, right? And other properties are going to be different as well. Even though formula-wise they're the same, they all have the same bonds, you know, platinum, chlorine, platinum, nitrogen, platinum, nitrogen. It's just oriented differently in three-dimensional space. This one is very famous, though. This molecule is called cisplatin. And cisplatin is an anti-cancer drug, called chemotherapy, chemical therapy agent for cancer, many different types of cancer. And the discovery of this is really interesting because the discovery of this was the group at the University of Michigan was looking at what happens if you put a electric field that is a voltage on cancer cells. You know, does it inhibit their growth or do anything? So they got platinum electrodes because platinum is fairly inert. They stuck the platinum electrodes in the cancer cell medium and then cranked up the voltage to see, you know, will the volts screw up their growth or inhibit it or do something, you know, electric field, magnetic field. And it turned out that the platinum electrodes started reacting with the medium. That's very weird because the oxidation potential of platinum is very low. It's hard to oxidize platinum. That's why platinum is chosen as a metal of choice for electrodes. It's a very expensive metal, but it doesn't react with much. But whatever was reacting killed all the cancer cells. And so they wanted to figure out what. There's some kind of platinum compound that's forming and it's killing all the cells. The problem is you got a very complicated mixture and they generated, what do you think the yield of that was? It probably was a high percentage yield, but the actual yield was very small. They probably generated a tiny amount of this platinum containing compound. And so to separate that mixture would have been too much work. So they didn't even bother trying to separate the mixture and isolating the compound, the active ingredient in that. And so do you know what they did? This is very crafty. They bought every single platinum compound that they could buy from all the chemical companies. I don't know if they just used one, but this is how, you know, I don't know all the fine details of this, but essentially they just bought a whole bunch of platinum compounds and then just tried them one by one and see if they had the same anti-cancer effect. And the one that did was this one here. And so cisplatin was discovered. That's the discovery of cisplatin. Cisplatin has sold, I think, like billions of dollars worth of this have been sold. Yeah. It's a University of Michigan held the patent on that. So that was and it's very good. I mean, of course, for people's health as well. But very good. So then, anyway, these are what we call cis here and trans here. None of these are optically active. One way we can tell if there's optical activity is if you can cut the molecule in half and get two equal. So if we cut the molecule in half here, we get two equal halves, or if we cut it in half here, we get two equal halves. That's called a mirror plane. And so if you can cut it in half, it has a mirror plane. If it has a mirror plane, it's not optically active. Same thing here. We can cut this in half right here, horizontally, and we get two equal halves. That's a mirror plane. It's not optically active. This one has a mirror plane too. I don't even have to draw the mirror image. I know this is not going to be optically active because you can cut this in half along the plane of the screen. As well as this. This is not going to be optically active. So these have no optical activity. Okay, now if we have three of a kind, we can place the three on the face of the octahedron, or we can place the three on the edge. If we put the three on the face, it's called the facial isomer, and if we plug it on the edge, it's called the merdinal. Neither of these would be optically active because you can slice these in half. And so you just look, and you slice in half and get two equal halves. That's one way. The other type, those are geometric isomers. Then we have the optical isomers. The optical isomer, the origin of the name optical isomer comes from the interaction of light. It depends on the orientation. You know, let's say the light interacts with your thumb. So if the light interacts with your thumb, then it's going to be twisted this way. You know, light interacts with electrons, and so and your right thumb, it's going to be twisted the opposite direction. And so one's going to twist it this way, the other's going to twist it the other way. We give little you know, there's different. There's more to the nomenclature. You know, and there's R, S, et cetera, et cetera. We aren't going to get into that. Essentially, with a triethylene diamine or we have oxalate, the triaxylate, these are going to be optically active. Even with the dioxalate or bisethylene diamine, this would be trisethylene diamine. These would be optically active. If you try to cut this in half, you aren't going to get two equal halves, no matter where you cut it. And the halves are going to be this, so there's no mirror plane in this. Same thing with the box, you know. This is not optically active, that's the same, but this is optically active, you know, because if we try to twist this is open top box here. If we try to twist this, then we can't line up the blue. Yeah. This is very important in biology. It's probably the most. So a lot of people try to synthesize, you know, like ibuprofen. You know. Ibuprofen, say if you synthesize a ton of ibuprofen, half a ton is wasted. Half a ton is wasted because only half of it is biologically active.
So do they just like throw it out or they're?
No,
You can only synthesize one.
they don't even separate it because it's not worth separating. But I guess they could separate and recycle material. You know, it depends on cost effective, whatever. So a lot of people are trying to have what's called stereoselective synthesis. Stereoselective is just synthesizing one of these. Usually what you end up with is a racemic mixture. Racemic mixture means 50-50. That's because when you make a bond, you have a 50-50 chance of linking it here or linking it there. You know, they're just reacting to things. And so most of the time we form racemic mixtures. Racemic mixtures are optically inactive because what happens is it twists one way and then it twists the opposite way, and then it cancels one another out. And so if I put a racemic mixture here, it doesn't twist it. And so that's a lot of ways. So a lot of people try to synthesize only one, and that would be stereoselective, but it's not so easy to synthesize only one. You need ways to get it just one thing. So this is one of the ones we did. This is actually turns out that the was it the trans or the cis? I can't remember. It was this trans isomer of this was optically inactive, and the cis isomer was optically active. So there are three isomers of this. Two cis isomers, you know, one is like a right-handed form, the other is like a left-handed form, but one trans isomer. So three isomers for this that we built in lab the other day. There's one other thing about complexes, transition metal complexes in particular, is they have interesting optical, that is color, and magnetic properties. And so these interesting optical and magnetic properties arise from what's happening with the d orbitals and the d electrons. And so if you look at like ruby, ruby consists of colorless, mainly colorless compound, but there's some transition metals in there that give it color. And the origin of the color there, and the origin of the magnetic properties comes from something called crystal field theory. And so I just would briefly want to talk about crystal field theory. All you need to know is crystal field theory deals with the d orbitals. And what happens when you bring the ligands in, the ligands interact with the d orbitals differently. depending on if the ligands come straight into the d orbitals or if the ligands come to the side or in between the lobes of the d orbital. So this is what we call an octahedral field of ligands. So we have a 6-coordinate compound with 6 ligands in there. And what happens is the d orbitals are normally degenerate. They have the same energy. But if we bring an octahedral field of ligands, then they split. So the XY, the XZ, and the YZ are lower in energy. All of them are higher in energy because we got electron-electron repulsions, the orbitals hold electrons, and the ligands are electron pair donors. But the Z squared and X squared minus Y squared are hit head on. And so ligand comes straight into this lobe. If there's an electron there, then we're going to get electron-electron repulsions here. And the Z squared here, you have this hula hoop that gets it head on with these ligands over there. Whereas if you look at the XZ, the ligands come in between the lobes. So the repulsions aren't as great. So that's why these are a little lower in energy, but all of them are higher in energy. And so this is what happens. This is called a free ion, and then when you bring the ligands in, it causes repulsions, which increases the energy, and they increase unevenly. It also depends on the ligands. Some ligands interact more strongly with these. Those ligands that interact strongly are the carbon and the nitrogen donors. Yes. Then we have the oxygen donors, and then the halides over here. And so these halides here react weakly, whereas like something like cyanide reacts strongly. And so what we see is this is called delta. This delta is called the crystal field splitting energy. And so we split it either big with these ligands, like cyanide or nitrogen, ethylene diamine is a nitrogen donor, pyridine is a nitrogen donor, ammonia or amine, EDT is an oxygen donor, thiocyanate is a nitrogen, water, oxygen, oxygen, oxygen donor, and then the halides. That's in general. Well, the splitting is going to change things. Like it turns out this splitting is in the visible region. And so if we have an electron here, the visible light will hit that and promote it up here. And so a lot of these complexes are colored. And depending on the splitting, the larger the splitting, the higher energy visible light that's required. And so it depends on, like here, we have aqua. And the chloro. Or actually, that's probably not the easiest example to see. But there's going to be color. Now that's with the octahedral. With tetrahedral, splits it differently because the ligands come in differently. And square planar splits it differently. And so octahedral has this kind of pattern, tetrahedral has this, and square planar has this pattern. So there are different splitting patterns here. The splitting pattern is going to influence certain things, especially the magnetic properties. But the color is going to be influenced by these delta gaps here, and whether it absorbs in the blue region or the red region of the visible spectrum is going to change the color. But how it splits will definitely influence the magnetic properties like here. So if you have fluoro, this is the hexafluorocobaltate, versus amine. Amine, a nitrogen donor, is going to split it more intensely, whereas fluoro doesn't split it much. Now this gap isn't huge, and so normally we have all the off-bound principle. Remember the off-bound principle? Off-bound just says you fill the lowest energy orbitals first. But here, what we do is we have to weigh this. When we pair an electron, there's electron-electron repulsion, and that leads to something called the pairing energy. So we have to compare the pairing energy to the splitting energy, the delta. And so over here, the pairing energy is greater than the delta, the splitting energy. And so what happens is we have 6 electrons, And we fill it 1, 2, 3. The fourth one gets promoted because delta is smaller than the pairing. And so it fills like this, 1, 2, 3, 4, 5. Okay, once we fill all these orbitals singly, then we have to pair it. So we have to break down and pair this one here. But that's because this energy gap's not so big. Whereas here, the energy gap is bigger. And so what we'll do is we're going to pair it before promoting. And so 1, 2, 3, the fourth one pairs, fifth one pairs, sixth one pairs. And so this gap is too big here. And therefore it fills normally. And so this is abnormal, this is weird because we're promoting it. And the only reason we're promoting it is because delta is not so big. But it gives these two totally different magnetic properties. Even though we have 6 electrons going into the d orbitals, this one has 4 unpaired electrons, which means it's very paramagnetic. This one has no unpaired electrons, which means it's diamagnetic. Diamagnetic means all the electrons are paired. And so this is highly paramagnetic, this is diamagnetic. This one's repelled by magnetic field, this one's strongly attracted. So this one would be like this one would be like this one. You turn on the magnetic field and boom, this one goes. All right, so this is called high spin. High spin means, you promote. This is called low spin. Low spin means you pair. All tetrahedral complexes are high spin. The rest depends on what the ligands are. Yeah. We'll see some examples of this. But that's crystal field theory is something that helps you understand the color of some of these, like especially gemstones. In fact, this chapter started off, actually I didn't put the initial. This chapter started off talking about colors a little bit, and the origin of the colors here. And so it depends on the splitting energy. They're going to yield different colors depending on what color light is absorbed. And so these are this is the aqua complex of copper, which is blue. However, the chloro complex of copper is yellow. It's kind of weird. Why is the copper 2 blue here and the copper 2 yellow here? And it's because the splitting energy is different because chloro and aqua are different ligands. So that's split. And you just have to have a good chapter. So that was pretty much chapter 24. We'll look at some example problems in the Zoom session for that. Chapter 25 deals with nuclear chem. Nuclear chem plays by a whole different set of rules. Nuclear chem and nuclear chemistry deals with the nuclei. And nuclei, you have ones that are exceptionally stable. Like this is a very stable nuclei. But one single nuclei is called the nuclid. So this is one stable nuclid. And we have 2 protons, 2 neutrons. This is the nucleus of a helium atom. Helium has an exceptionally stable nucleus, but is a carbon nucleus equally as stable? No, there's slightly different stabilities depending on the things. It turns out that helium is quite stable. Carbon is here. Actually, carbon. Did you know carbon nucleus is more stable than a helium? Well, that's what it's showing here. Carbon's more stable. Oxygen's more stable. Neon's more stable. You know what is about the most stable nucleus on the periodic table? The most stable nucleus is going to have a mass number around 60. So what has a mass number around 60? When we look at the periodic table, the mass number around 60 is going to be around here. Mass number would be the protons and neutrons. So, we've got 28 protons, 29 protons, but the average atomic mass is around 59, average atomic mass around 64. So around here is going to be the most stable nucleus. Most stable nucleus. Iron. Yeah. And so it turns out that that here's the most stable. And so the lighter nucleids are less stable, and the heavier nucleids are less stable. Okay. And so it turns out that in nuclear processes, we try to fuse lighter nuclei. That is, you can get two lighter nuclei to fuse together to make a heavier nuclei. And it's called nuclear fusion. So nuclear fusion is energetically favorable for light nuclei. And so the sun operates off nuclear fusion. What the sun does is it takes hydrogen atoms and then fuses them together to form helium. And so if you take the nuclei of hydrogen and fuse it together to form helium, that's more favorable in terms of energy. And this is the stability here. Higher stability. Whereas heavier nuclei, like over here, will tend to want to undergo fission processes. Fission processes, you break them apart. But, so that's in general. But let's take a look at nuclear stability in more detail here. And so these are the observations, patterns, and trends that we see. It turns out there are magic numbers. Do you see these peaks here? These peaks here correspond to magic numbers. Magic numbers are this. If the number of protons is 2 and the number of neutrons is 2, that's a magic number, and that's an exceptionally stable nucleus. If we have 8 and 8, that's oxygen, exceptionally stable nucleus. 20, that's neon. 20, 28. And so these are exceptionally stable. This is the observation, experimental observation, because you can determine what the stability of the nucleus is. But the thing is, okay, so we have the observations, we see a pattern there, there's a pattern there. And then what do? You look for some hypothesis, why is there this pattern? So one of the hypotheses that was proposed is these are like shells, like electron shells. You have a filled first shell, second shell, etc. That's one of the hypotheses for this. There's another observation that's seen, and that is if we have an even number of protons and an even number of neutrons, then that appears to be stable because 163 of the nucleids are like that. Whereas if we have an even number of protons and an odd number of neutrons, there's 55, and then an odd number of protons and an even number of neutrons, there's 50. But if we have odd, that seems to be the least favorable. And so this is called the even odd. Even's the best, and then it goes down from there. And so what's the hypothesis you might generate for this? What is that? So there are different hypotheses. These are just, remember, observations. And then there's something called the sea of stability. The sea of stability is the neutron to proton ratio. For lighter elements, we like to have a 1-to-1. As it gets heavier and heavier, we like to have about a 1.1-to-1 ratio, and then it's stable. If you're outside the sea of stability, then it's radioactive, basically. And so, for example, oxygen has 3 stable isotopes, oxygen 16, oxygen 17, oxygen 18, but it has a ton of other isotopes that are radioactive. And the ton of other isotopes are ones with odd neutron to proton ratios. And so you could throw out something out here with too many neutrons, or you could throw something out here with too many protons, and that will become radioactive. And so the sea of stability are these non-radioactive nuclei, and then outside the sea of stability is the radioactive species. Let's see. So there's an island of stability up here, which is missing on this one. So this is the sea of stability and the island of stability. Okay. But one of the hypotheses is this. As the nuclei become bigger, you need more neutrons. And one of the ideas is the neutrons are like the glue that holds the protons together. And so you need a little bit more glue. And then eventually you get to too big. Once we get to, let's say, 80 protons, they all become radioactive until we get to the island of stability. And this is just too hard to hold 80 protons together, or more than 80 protons together. So once we get to about here, polonium, they're all radioactive beyond that. And so bismuth is about it. And then it's about as big as you're going to get. And then they'll become radioactive until you get to the island of stability, which has these things. And so we have radioactive isotopes for everything in the periodic table, depending on the proton to neutron ratio. Like carbon-14 is radioactive, P32, phosphorus-32 is radioactive. A whole bunch of them. A lot of those are man-made, others are natural. So when we have a nuclei that's too big, like uranium, the uranium-235, too many protons to hold together, hydrogen repulsion. And so what's going to happen is a chunk of this uranium is going to break off. And so the neutron comes in here and destabilizes this, and a chunk breaks off here and makes smaller nuclei, which are going to be more stable. But it's actually a long process here. So this is U-235, this is U-238. And so this is called a decay series for U-238. We have different decays. The pink ones are a chunk of the nucleus breaks off, and this chunk consists of 2 protons and 2 neutrons. 2 protons and 2 neutrons are helium nucleus. And that's called an alpha particle. And so this is alpha, and then the blue ones are beta. Beta particles are electrons, but these are electrons that come from the nucleus. Now, how can an electron come from the nucleus? Because the nucleus doesn't have any electrons, right? The nucleus doesn't have any electrons, but how an electron comes from the nucleus is a neutron gets converted into a proton. And that's a nuclear reaction. So if we take an alpha particle, just a chunk breaks off here. A beta is when we convert a neutron into a proton. So let's say we have too many neutrons, not enough protons. Well, then beta emission is a good candidate for that. So if you have too many neutrons, not enough protons, you can convert a neutron into a proton and a beta. And there's some X-ray or gamma radiation that's also associated with this. And so an example would be thorium-234 gets converted into Pa-234. But a proton gets converted into a neutron gets converted into a proton, so Z increases by 1 in the beta particle. Now, nuclear reactions are easy to balance. If you look at this, 92, this is 90 plus 2 gives us 92, and this is 238. 234 plus 4 gives us 238. Same thing here, we have 0 as Z, and so 1 plus minus 1 gives us 0, and 1 for the mass number, 1 plus 0. Over here we have 90, so 91 minus 1 is 90. 234 plus 0 is 234. Electrons have no mass number. We can also have positron emission. So this is beta emission. This needs the beta. This is positron, which is a positive electron. And so a proton can get converted into a neutron with a positron emission here. You don't have to memorize these. There's something else called electron capture, where this is a core or inner shell electron, and it's captured by the nucleus. It converts a proton into a neutron. This is going to be followed by X-ray emission. And so this shows the 3 types of radiation that we encounter: alpha, beta, and gamma for X-ray, which is just white. Alpha and beta are particle radiation, and gamma and X-ray are electromagnetic radiation or light. Electromagnetic is not shown here, so alpha, beta, beta, alpha. And that's going to change the mass number and Z. So eventually this decays. This is called the decay series, and eventually it decays to something stable. And what that something stable is lead. The problem is it takes a long time. The half-life for lead formation is like over 4 billion years. So it's going to take a long time for the uranium to decay to lead, but eventually it will decay to lead. We can measure radiation using a Geiger counter. Geiger counter is, these are called ionizing radiation. Ionizing radiation because when they interact with matter, they knock electrons off. And so what we have is we have a neutral gas in here, and when it gets hit by ionizing radiation, it creates ions. Well, those ions can transmit electricity. So if we have one electrode here and one electrode here, there's nothing conducting electricity between the two electrodes until we form ions. Once we form ions, then the ions can conduct electricity, and we get a signal. So this is a Geiger counter. Geiger counters work well for beta and gamma and X-rays. But Geiger counters don't work very well for alpha particles. Alpha particles are kind of bulky. And alpha particles are, if you think about what has the highest reduction potential on our chart, on our redox chart, the species with the highest reduction potential on our chart is fluorine. And so what we say is fluorine is the most powerful oxidizer on our chart. It has the highest reduction potential, almost 3 volts. But do you know what alpha particles would rank? Much, much higher. Alpha particles are going to have a huge reduction potential because they're so unstable. So alpha particles are the most powerful oxidizer that I can think of. And the problem is alpha particles are gas, and so do you want to inhale fluorine? No way. You wouldn't want to inhale fluorine because it would cause a lot of damage. Well, if you inhaled alpha particles, you're looking at much more severe damage. And so alpha radiation is very dangerous because of that. It's very dangerous because it's extremely chemically reactive. Alpha particles, the danger of them comes from their chemical reactivity. They're such a powerful oxidizer. But they're radioactive. Alpha particles themselves, are they radioactive? No, they've got a very stable nucleus. But they're radiation, aren't they? Yeah, they're radiation because they come from radioactive. They're generated by emission from radioactive isotopes. So the alpha particles themselves are not radioactive. They're just extremely powerful oxidizers, and they're very dangerous because of that. Plus, they're gas. But alpha particles, it's very easy to shield yourself because all you need is a piece of paper. This paper is a good reducing agent. So if you have oxidizers like this, you can shield yourself with paper. That's all you would need to shield yourself from alpha particles. Well, can you use a piece of paper to shield yourself from gamma radiation? No, because gamma radiation would pass right through it. And so in that sense, alpha particles are very damaging, but they're easy to shield yourself. More damaging than gamma rays potentially.
For gamma rays, they mostly use lead, right?
Yeah, they use lead. For X-rays, they'll use lead, like, you go to the dentist and they'll have a lead blanket. For gamma rays, you need a lead brick. They calculated how thick of lead do you need. And so usually you have a brick that's like 4 inches thick, and that should protect you pretty well from gamma radiation. So when I was working with a gamma radiation source, it's surrounded by lead. Yes. There's a guy at UCSB. He was studying the ATP, ADP. What happens when he exposed, I think, yeast to gamma radiation, and then looking at the metabolism there or something like that. I forgot, or bacteria. And so he's working with a lot of gamma sources. So I thought that was pretty interesting. Anyway, going back to this here. We need lead. What about beta? Beta are electrons, these high energy electrons. And these electrons can cause ionization as well. You get high energy impact, you can create species, or if the electron gets captured by an atom, forms an anion. Ionizing too, but for beta, it's easy to shield because aluminum foil, aluminum foil is a good shield for beta radiation. So.
Is that the origin of people wearing aluminum hats to protect themselves from aliens?
I think so. No, I don't actually. I don't know. But yeah, you can do that. You can shield yourself. Actually, we're out of time. So it's just going to be a brief survey of nuclear chem. So I just need to finish